Today, construction of the simple Lie algebra with given carton matrix. A. So before getting to that, we have a short digression on adjoint functors. So consider the category of Lie algebras. So this is my category Lie. And we have a category of sets. And we have a functor that takes a Lie algebra, which is some vector space over a field K. And it has a bilinear operation, which is the bracket. And you just give me back the set G itself. And this thing is a nice functor because if you give me a morphism from G to G prime, then you get a map of sets from G to G prime, and this is compatible with compositions and everything. So let me call this functor the forgetful functor. It just forgets the bracket and the linear structure. It just remembers the set G. So theorem, which I'm told Jethro is going to prove next class, is that this functor has a left adjoint let me call it F, not for forgetful, but for free. So this is a functor from the category of sets to the category of Lie algebras. Well, as stated this way, this can't possibly be because Lie algebras are vector spaces over a field. So what is the field here? And you realize that actually we can just consider not arbitrary Lie algebras because I don't know how to define morphisms between Lie algebras. So Lie algebras by itself is not a category. But Lie algebras over a fixed field, they are. So if I fix K, then Lie algebras over K form a category. These are morphisms of K vector spaces that intertwine their brackets. And for each K, I have a functor, an adjoint functor, from sets to Lie K. So what is this left adjoint? So here, definition is that two functors are adjoint. In this particular case, I'm only going to use this F and the forgetful functor. This adjointness means so perhaps here instead of definition, this is a remark that for every pair of X a set and G a Lie algebra over K, there's a natural isomorphism between the set of homomorphisms from, so in the category of Lie algebras, from the free Lie algebra associated to X, so this is F applied to the set X, and G, and this is isomorphic to the set of homomorphisms in the category of sets between X and the forgetful functor applied to G, so G as a set. Moreover, this isomorphism is natural. This isomorphism is natural in the sense that it's compatible with morphisms on either side. Namely, if you're given a map of sets from X to Y, so this is a morphism in the category of sets, and you're given, well, so if you have such a thing, then, well, you do have an isomorphism from the free Lie algebra of X to G. This is in the category of Lie algebras. And this is the phi that corresponds to this pair, X and G, to X G, here in the category of sets. Now, from something is a contravariant functor. So you have a map Y. So if you call this map I, this is the composition with I. This in the category of sets. And F is a functor. So if you have this, then F of I gives you a map from F of X to F of Y, and this is F of I. And since hom is also contravariant in this category, you get a map hom of F of Y to here. This is the composition with F of I G. And here is the phi that you get for the pair YG. And this diagram commutes. And similarly, if you are given a morphism of Lie algebras, for a morphism G to G prime, you're going to get some compatible diagram like this. Okay? So that's what an adjunction means. But concretely, this characterizes a universal property of this Lie algebra f of x. So let's read what this isomorphism phi is. So that's a universal property is that for every morphism, for every map of sets, from X to some Lie algebra G, there exists a unique, so a map of sets F from X to G, there exists a unique map of Lie algebras F of X to G, F bar, map of Lie algebras, such that the following diagram commutes, and I need to tell you what this map is. Well, this is the one that exists, actually, and is unique. And this is the arrow that I need to tell you what it is, a map from X to F of X, such that this commutes. So now, what is this map from X to F of X? Well, F of X itself is a Lie algebra. So I can take G to be F of X. So if in this definition of adjunction I take G to be the Lie algebra F of X, then the isomorphism gives me an isomorphism between Lie algebras, between F of X and F of X, and an isomorphism of sets between X and F of X. But this set here is a pointed set. The identity homomorphism of F of X is an element here. Therefore, to this identity, it corresponds an homomorphism of sets from X to F of X here under that isomorphism. So that guy, let me call it eta. And that eta depends on X, of course. So I should probably call it eta of X. So this guy here is eta of X. Okay, so this is the universal property of this free Lie algebra f of x. And the theorem asserts that this functor exists, that this f of x exists. The construction given in lecture is for free R modules. So let me just repeat that construction. So similar examples are in many different categories, many different algebraic categories. So similar situations are, for example, when you fix R a commutative ring, a unital commutative ring, then you have a functor from the category of R modules to the category of sets that just takes a module M and it just remembers. So this M is a set with an action from the ring. So let me call it this multiplication. And this set is an abelian group, so it remembers the plus, and it has a 0, and it has a bunch of structure. And I forget everything, and I just remember the set M. In fact, well, you can adorn this a little bit more by just mapping only to abelian groups and forgetting the action, for example. But anyways, so this is a forgetful functor. It forgets the structure. It forgets the action. It forgets the addition in M. It forgets the 0 in M. It forgets a bunch of stuff. It only remembers a set of elements in M. And this functor has an adjoint. There exists an adjoint functor, a left adjoint again. Let me call that functor F as well. And this one we can construct explicitly. Given a set X, a set, then you construct M as the direct sum over all elements X in X of the free module R. So this is the same thing as R raised to the X compactly supported. So by this, yeah, probably that's a bad idea. Let me use finite. So this is a set of functions from X to R that are compactly supported or with finite support. Functions from X to R that are 0, f of x is equal to 0 almost everywhere, in all but finitely many x. So this thing here is an R module. It's clearly an R module. If you give me, well, this thing here is an abelian group. If you give me two functions, f and g, in f of x, then their sum, f plus g, evaluated at x, is just simply f of x plus g of x. And since for all but finitely many of x's, f and g are both 0, then this thing is for all but finitely many x's 0. So this is an element in f of x. Associativity, commutativity, and so forth, and the 0 function for this is obvious because it follows from the existence of the corresponding object in R. So in particular, the 0 element of f of x is the function 0. This is the function in f of x, which is a 0 element, and the action of an element in the group. So if you give me alpha in R and f in f of x, then you just declare the action to be alpha f, which is the new element in f of x that evaluated at x is just alpha on f of x. The multiplication in R is what you're using. So that gives you a module, and now I need to check that this module satisfies this isomorphism here. So if you give me any other module, an R module, I need to give you this isomorphism here. So I need an isomorphism between HOMs in the category of R modules now, between the free module generated by X and N, and HOM in the category of sets between X and N. Okay, so I first realized that I have my eta. For that definition of f of x, I have a well-defined eta of eta x, which is a map of sets from f of x, from x to f of x. That's the eta that I have there, now in the category of R modules. What is this map? Well, for any little x, it needs to give me a function from x to R. And that function is going to be the characteristic function of x. Well, my chi's and my x are the same. But this is the function that is the characteristic function of x. This is the function that is evaluated on y is equal to 1 in the ring if y is equal to x, 0 otherwise. That's a well-defined function from x to this f of x that were compactly supported function. This function has support at only one point. And I'm going to exploit this to construct this isomorphism here. If you give me a module n and a function here, and a phi is a bad idea. Let's say that you have some s, which is an homomorphism of R modules from f of x to n, then you can restrict. You need to get an homomorphism of sets here. So if you give me x, you need to give me now an element in n, and that element in n is going to be s of eta of x. So that is this map that goes from s to this guy, okay, to this function. And I need to check that this map is an isomorphism. And it's an isomorphism of sets, so it's a bijection. So if you give me an homomorphism of sets here, I need to produce an homomorphism of R modules. Okay, so let's suppose that you give me an homomorphism of sets. Let's put a name to an homomorphism of sets. I guess T. And I need to produce where that guy goes. Okay? So I need to give you now an homomorphism of R modules. So an element in f of x is a function f. And I want to send this function to an element in n. Okay? And the question is, what is that element in n? But this function f, and what I know is how to send elements from x to n. Okay, so this function f, I can send it to the sum over all x in x. So this is a sum, the set might be infinite. So this sum in principle is an infinite sum. But what I can do is just take f of x, which is now an element, in the ring, and then I can multiply this by t of x, which is an element in n. So this guy, by definition, is an element in the ring. This guy, by definition, is an element in n. This sum is using the sum in n. The symbol sum is using the addition in the R module n. This multiplication is using the action in the R module n. And the fact that this sum is well defined in n is because f of x is supported in finitely many x. So for all but finitely many x, this thing is 0. So this is a sum that is a finite sum. And it's trivial to check that this thing is compatible with the R module structure on both sides. So if I multiply this function f by alpha here, then I am multiplying each one of these guys, which is the same thing as taking an alpha outside, and that's the action on n. And if I take the sum f plus g, it's the same thing as just summing up there. So that's a proof that this is the adjoint functor. And that's the free module generated by a set. For Lie algebras, it's slightly trickier because Lie algebra satisfies some axioms. You need to check that you're going to satisfy Jacobi and that you're going to satisfy the skew symmetry condition. Here, our modules do satisfy some identities, and we needed to check that this R module f of x that we constructed satisfy and has an addition and it has an action. But then the properties of the addition and the properties of the action were inherited from the similar properties of R itself, which is an R module over itself. So for Lie algebras, that's not exactly the same. And I suppose Jethro is going to prove the existence of free Lie algebras in the next class. Notice, however, that whatever adjunction you're taking, if there is, if one adjunct exists, then it's unique up to unique isomorphism. So the free Lie algebra f of x, if it exists, it's unique up to isomorphism. Well, the diagram that we have is this. So let's suppose that we have two f of x that satisfy the same property. Suppose that you have some f of x and some other f prime of x with the same properties. So that means that you have some eta x here and some eta prime x here. And for any Lie algebra G, you have a unique and a map of sets here. F is a map of sets. There's a unique F here, F bar here of Lie algebras. Okay, so that's the universal property of this f of x. And then there's a unique f prime bar here. I guess probably it's like this. Okay, so I want to prove that these two things are isomorphic. And this is very trivial because you can just consider this diagram for G equal to f prime of x. That's a Lie algebra. So for G is equal to f prime of x, you have a unique isomorphism from f of x. So you look at f of x, you have eta of x, you have here f tilde of x, and you use eta tilde here. And then this universal property tells you that there's a unique map here making this diagram commute, and this map is eta tilde bar. On the other hand, this is now the universal property for f tilde of x applied to G being f of x, and here the map eta tells you that here there's a unique map which is eta bar, making this diagram commute. But on the other hand, I can use now again the property for f for the Lie algebra G being f of x. So if the Lie algebra G is f of x and I use eta of x here for f and here, then there's a unique map making that diagram commute where here I have eta and here I have eta and here I have f of x and here I have f of x. I know what that map is. It has to be the identity of f of x. So that means that the composition of this map with this map is the identity on f of x. And similarly, if you just extend this by the universal property of f of x, you're going to get that the composition of this map with this map is also the identity on f tilde of x. So that's why these two are isomorphic. And this holds for any time that you have these sort of adjunctions. Okay, so let's use that we have this adjunction to prove that we can construct a Lie algebra starting from a Cartan matrix that has that Cartan matrix as Cartan matrix. Okay, so let's start with the Cartan matrix A with associated Dynkin diagram D. And Well, so this has a bunch of nodes, so or this has a bunch of nodes, so let's say that the set i's are the nodes of D. So this is a finite set, and let's just consider a bunch of elements. Let's consider the set EI's, FI's, and HI, where I is in I. So this is a finite set that has 3 times the number of elements, the number of vertices of D. Okay, so this is a set. Let me call this set X, which is going to be the disjoint union of X plus, disjoint union with X0, disjoint union with X minus, and here the EI's are going to be here, the HI's are going to be here, and the FI's are going to be here. So consider the Lie algebra G tilde of A is the free Lie algebra F generated by that set X. Perhaps that's a bad name. Let me consider this. Yeah, I'm not really sure what's. Perhaps I shouldn't even give a name to this thing. I don't remember what names Jethro used in his note, but I'm pretty convinced that it's not G tilde of A. So let me just change this name and let's use something like G huge. Let me use something like G hard. Just to use a name that I'm sure wasn't used in Jethro's. Okay, so this is the free Lie algebra generated by this set X. Okay. Now, in this Lie algebra, I'm going to construct an ideal. And that ideal is going to be generated by a bunch of relations. So I'm going to declare that EI bracket, well, actually, no, I don't want to kill that. I want to kill this. I want to kill that HI bracket AJ is 0. So I'm going to declare that this is in the ideal I. I'm going to declare that HI bracket EJ, well, not equal, but is equal to AIJ EJ. So this is the entry IJ of that matrix A. So this is an integer number. And I'm going to declare this to be in the ideal. So that's equal to 0 in the quotient. And I'm going to declare that HI bracket FJ is equal to minus, so I'm going to put a plus AIJ FJ. So that's also going to be in the ideal. And finally, I'm going to declare that EI FJ is equal to delta IJ HI. So this delta is 1 if I is equal to J, and 0 if I is different than J. No, the ideal is not the set of this. I'm just declaring this is a bunch of elements inside of this Lie algebra. And once I give you a bunch of elements inside of the Lie algebra, you consider the smallest ideal of this Lie algebra that contains these elements. So I is generated by these guys. So it's hard to prove that free Lie algebra. Well, it's not hard, but you need to prove that free Lie algebras exist. But you do not. I mean, it's trivial to check that there is such an ideal, because you could just consider the set of ideals of G containing this. This is an ordered set. It's non-empty because f of G itself is there. And these elements, so you just take the smallest one under containment. So it's trivial to check that such an ideal exists. And that's the ideal generated by these elements. We have no control over what that ideal is. That's why it's hard to check that the quotient is anything meaningful. It could be 0, for example, the quotient. So let's try to prove that the quotient is at least not 0. But now let's define the Lie algebra G tilde of A to be the quotient of G heart of A by I. Okay? Okay, so the claim is that this guy here, well, similarly, so now we have some maps from the free Lie algebra generated by X plus. We have a map to GA hard. That's the free Lie algebra generated by X. This map corresponds to the map of sets, which is X plus is inside of X, and X came with a map to f of X. Probably I should just keep using f of X instead of GA hard. GA hard is just f of X. It's the free Lie algebra. So this is the eta X. And this composition is a map of sets from X plus to this Lie algebra. Now by the universal property of the free Lie algebra generated by X plus, this gives you a map like this. And this map is unique. And now this guy maps to G tilde of A, because this is the quotient map by the ideal. So therefore you get a map like this. And similarly for minus. And similarly for 0. Okay, so I have these three inclusions of sets from X plus or X minus or X0 inside of X, and that gives me maps from the corresponding free Lie algebras to these guys. Let me call the images of these three Lie algebras inside of here N plus H and N minus. So this is the image of F of X plus, F of X0, or F of X minus in G of A, in J tilde of A. Okay, so this is the image of these three guys here. In practical terms, what are those? So I haven't told you how to construct the free Lie algebra, but an outcome of the construction of the free Lie algebra generated by a set is that every element of that Lie algebra is a linear combination of brackets of elements coming from the set. So a typical element of N plus is a linear combination of the images of elements like EI1, EI2, EI3, EIK minus 1, EIK, and then you start taking all the brackets. Okay? So you take a bunch of brackets from X plus, of elements from X plus, and you just take linear combinations. So what you need to prove is that there is a way of writing a bracket of two such elements in a unique way to get a Lie algebra, and that's why the free Lie algebra exists. It's trivial to check that brackets like this, so once you have the free Lie algebra, then this is an element in that free Lie algebra, because for each one of these EIAs, the eta of that is an element in f of x plus, and then you can just take the brackets like this. Then what it's not so trivial is to prove that every element is going to be linear combination like this, but then again, from the Jacobi condition and skew symmetry, it's easy to check that you can just put all of them put all the brackets towards one side. Okay, so the theorem we want to prove is that G tilde of A is a direct sum of N plus H plus N minus. And this is non-trivial. This is a bad idea to use these names. Let me use tildes since they are all inside of G tilde. So this is the important statement. A typical element of G tilde of A is a linear combination of images under the quotient map of elements like what? Well, they are going to be, a typical element here is images of elements like this, like xi1 bracket with xi2 bracket with xi k minus 1, xik, where these xi's are in x, are arbitrary elements in x. So they could be either an ei, an fi, or an hi. Whether a typical element here is a sum of three things, one involving only h's, the other one involving only e's, and the other one involving only f's. So I need to prove that any element like this can be written in this form, which is restrictive. It's clear that this direct sum, if it was direct, is inside. This is obvious. What I need to prove is the inclusion the other way around. And I need to prove that this sum is actually a direct sum. It's not obvious immediately that the sum is direct because I am quotienting by something. And that ideal might have cross terms, might identify something on the image of n plus with something in the image of n minus in principle. Right? See, if one of these relations was ei minus fj, then clearly that could not have been a direct sum. I feel like I've lost my voice. It's not really clear if it's, I guess no one's going to know if it's the game of Flamengo or the elections yesterday. Anyways. Okay, let's prove that this sum is, that this is a direct sum. So the first thing is, since this guy is written like this, then I'm just going to prove by induction. So any element here is a direct sum of elements like this. I'm going to be doing induction on the number in the number k. So you do induction in k, in the number of elements that you need to take brackets to construct this element in G tilde of A. So if you only have one element, then it's clear that it belongs either here, here, or here. Because this xi is either an e, an f, or an h. And if it's an e, it's here. If it's an f, it's here. And if it's an h, it's here. So let's assume that for less than k elements, then it is in that direct sum. Right? I want to prove the inclusion of this inside of here. So let's assume that whenever I take the bracket of k minus 1 elements, then it's in each one of them. I need to check that when I take k elements, a bracket of k elements, then it's still in that sum. So let's do for one case, and then you guys do the other one. But they're all more or less the same and trivial. So let's suppose that you have ei1 up to, well, ei2, I guess, up to eik. So these are k minus 1 elements. So k minus 1, eik. And this guy, by induction, is inside of n tilde plus. These are k minus 1 guys. And let's just take the bracket of some x with this. And I want to check that this is still here. No matter, well, I want to check that this, if it's not here, then at least it's in the sum. Okay? Well, if x is equal to some ei, then it's obviously in n tilde plus, and there's nothing to prove. That by definition is the bracket of elements in n tilde plus. If x is some hi, then I use the fact that the adjoint action of h of x is a derivation. So I'm taking the adjoint action of hi evaluated at this element, which is k minus 1 brackets. So this is the same thing by the Jacobi condition as the bracket of hi with ei2 bracket with the rest. So this starts with ei3 up to whatever it is, plus, and then I need the bracket of these two, plus EI2 bracket with the bracket of HI with the rest, EI3 up to the rest. And now this is equal to AI2, EI2. So this is in eta plus, into n plus. And this is in n plus by induction again on K. So this is the sum of two elements in n plus, so this is still in n plus. The last remaining case is the only non-trivial one, which is when AX is equal to Fi. So if X is equal to Fi, then I'm going to use the same thing. Let's keep the relations here. I guess I removed some. Hi, Ej, and this is Hi, Hj. So if X is equal to Fi, then I'm still going to use the Jacobi identity, and I'm going to get Fi bracket Ei2 bracket the rest, Ei3 up to Eik, plus Ei2, and then I'm going to have Fi bracket all of the other guys. Okay. So the problem is that this guy here is either 0 or something in H. So this is delta I2, H, I. Okay? And then I have a bracket of a bunch of brackets. So if this guy is non-empty, then this is a bracket of something in H with something in n plus, and then it's again in n plus, in n tilde plus. But if this guy was empty, then this is in H and not in n tilde plus. Okay? So this, in principle, is either here or in H. So therefore, this thing is in the sum of n plus plus H. Okay? So now I can do induction. I can say, well, this guy is in n plus, and this is in n plus or in H, and by induction, this is in n plus H. Okay? Well, actually, plus H, I don't need to take the H tilde. So again, by induction, these two things are in n plus H. So in these two cases, n plus was stable, but if I take X in Fi, then I no longer land on n plus, but I land on the sum, which is what I want to prove. The other cases are the same. So we know that this G tilde is a sum. Now I need to check that this sum is actually a direct sum. Okay? And to check that this sum is a direct sum, I'm going to write a decomposition of G tilde of A as eigenspaces for an operator. So I'll prove two things. So first of all, notice that H tilde is equal to H, which is just the direct sum over I of your base field, K, times Xi. Times Hi. This is clear because I typic an element of H tilde, which is in the image of, oh no, I haven't proven that. I can't prove that yet. But it's a quotient of this. This is going to be true, but I haven't proven this yet. So in principle, every element of H tilde can be written as linear combinations of elements in the image of things like this, where the brackets are by HIs. Now, if I have more than one, this bracket is already 0 because of the relation that HI is commute. So it's in the image of the map from H. So what I know is that there is a map from H, which is surjective into H tilde. And H is this sum. This is the definition of H. But I do not know that this is an isomorphism because in principle,
some of these hi's could be killed by passing through the quotient by the ideal I. Okay? So in principle, I could have hi in the ideal, and then when I map here, then some of h dies. Okay? So I need to prove that this doesn't happen. No, this actually is indeed an isomorphism. But what we're going to do is I'm going to look at the image of h in h prime, in h tilde, and h acts diagonally, it acts semi-simply on g tilde of a. So h acts semi-simply well, this is because it acts semi-simply in the sum. If you give me an element of h in the sum, well, we've already proven this. I can do this by induction. So then by induction in K again. So an element in H, you take some element in H, and you take some xi, and this guy can be either an ei, an fi, or an hi, and I need to check that the bracket of h with xi is a multiple of xi. And this is true. If this guy is an ei, then it's just another ei. It's aij, is a linear combination. This h is written as a sum of alpha I hi, and h bracket ej is therefore a sum of alpha I aij ej. So this is the same thing as an evaluation of, it's a linear functional on ej times ej. So it's linear on this ej's. And the same thing for the f's. It's just a minus sign. So that means that you have a decomposition of this G tilde A decomposes as an H module. Alpha is in some set. And these alphas are the eigenvalues. So, and this set is by linear functionals in H are the possible eigenvalues. Of the H action. Well, since the eigenvalues for each one of these HIs is the simple root alpha I, right? And we've just checked that just by adjunction, by the fact that the adjoint action is a derivation, then you just get the sum of all the eigenvalues for each one of these guys. So this Q here, it's easy to see what it is. Q is equal to Z pi, where these are the simple roots. Well, this doesn't really make sense now because I do not know what pi is. I didn't start with a Lie algebra. I started with a matrix, which was this AI. Okay? So I haven't told you what this pi is. But I constructed this vector space H. I constructed this vector space H explicitly. This was a direct sum of KHI. And I have these linear functionals that I guess I'll just write like this. Alpha I evaluated on Hj is equal to delta Ij, I guess. Oops, sorry. I have this. I have hi on ej is equal to aij ej, and this I'll define it to be alpha alpha j evaluated on hi multiplied ej. So this is the definition of this alpha j. This defines this linear functional alpha j's for every j, and these are alpha j's are elements on H star by definition, and these are the pi's. Okay, so pi is the collection of alpha I for I in I, and now it's well defined. You can check that delta, well, let's construct delta later. We don't need the delta for the moment. But I have this diagonal action of H, of that Lie algebra, which is a commutative Lie algebra, H, on G tilde of A. So the final thing is, there exists an element H, this is a fixed element H, in that Lie algebra that acts, well, they all act diagonally because we have this decomposition, but I'll require that alpha of H is positive when alpha is in Q plus, and is negative when alpha is in Q minus, and is 0 on H. Well, just 0 on H acting on H is equal to 0. So I need to tell you what Q plus and Q minus are. So Q plus is going to be the linear combinations with positive coefficients on pi, and Q minus are going to be the linear combinations with negative coefficients on pi or minus Q plus. So that is, if I take G tilde of A alpha, and I sum over alpha in Q plus, in particular, all of N tilde plus is there because the EIs have positive action of HIs. Then I want to construct an H that distinguishes the positive part and the negative part from by eigenvalues. Okay, so that's very simple. I need to construct an element H that is positive on all these n plus, and negative in all of the n minus. So what I need is some H that evaluated. So I'm trying to solve for H, which is the sum of alpha I, HI, and I need to solve that H acting on EJ, which is the sum of alpha I, AI, J, EJ. And I want this sum to be positive. Okay? Well, you can actually make it so that it's actually 1. So you can solve the system in such a way that this is actually 1. So instead of positive, we can solve it to be equal to 1. And we know that we can solve it because this is a linear system of equations. I'm looking for the alpha i's, right? So this is the datum. This is the matrix, the Cartan matrix A. And I'm trying to solve this linear system of equation, which is the sum of alpha I, Aij is equal to 1 for every j. And A is an invertible matrix. So I actually gain something more. I have this element h, and the eigenvalues by the adjoint action on n plus, a typical element in n plus is a bracket of elements of k elements of the form ei's. And the eigenvalue is going to be k. For each one, I pick up a 1. So it measures this depth. So now the decomposition by eigenvalues, by the eigenvalue decomposition, we know that the intersection of n plus with h, which is the eigenvalue 0, is 0. The intersection of n plus with n minus is 0, because this is positive eigenvalues and these are negative eigenvalues, and the intersection of n tilde minus with h is 0, because this is eigenvalue 0 and this is a negative eigenvalue. So the sum is right, and we proved the theorem. But moreover, we've checked that we have this decomposition now by eigenvalues of the diagonal action of h, and we now have a very control of what the ideal was. So let J be an ideal in G tilde of A, a Lie-Algebra ideal. And let's suppose that D, the Dingin diagram of that Cartan matrix, is connected. Okay. Then I claim that if J intersects H non-trivially, then J is the whole Lie algebra. So if you have any non-trivial ideal that intersects non-trivially this image of H in H tilde, then the ideal is the whole thing. And this is actually how, I don't know if you did that exercise, but if you want to prove that SL3 is simple, that's essentially all of the technique that you use. So how does it go? Suppose that you have such an element. Okay, so let's suppose that you have an element H in the intersection of your ideal with H. So then this guy is non-zero by assumption. And then I claim that there's some EI, so there exists I, such that EI, well, you know that H bracket EI is a multiple of it, and I claim that it's non-zero. Okay. So here you use the fact that this diagram was connected. If this was 0 for every I, and this EI was a basis, then this would mean that H is 0. Since H is non-zero, then there's one EI such that this thing is non-zero. But this thing is always a multiple of EI. So this means that EI is in the ideal. So this is a non-zero multiple of EI. Therefore, EI itself is in the ideal because, well, this is an element in the ideal. But if EI is in the ideal, then that means that HI is in the ideal. Because you just take the bracket of EI with FI. But then that means that FI is in the ideal. Because you just take the bracket of HI now with FI. So now for just having this, you know that there is one HI such that the whole EI, FI, and HI are in the ideal. But now, that I corresponds to one node in the Dingin diagram. And the diagram is connected. So it means that there's some other node, let's call this guy J, that is connected with I. So that means that at least one entry, Aij, is non-zero. And if Aij is non-zero, then now, well, you have that H Ej is in the ideal. Because Ej
is now hi ej divided by this number. Okay, so this guy is this guy that is non-zero, and since this bracket is therefore non-zero, then this ej is in the ideal. And if ej is in the ideal, you play the same game. Hj is in the ideal, and fj is in the ideal. And since the diagram is connected, you just can get the whole diagram. So you get all of the EIs, all of the FIs, and all of the HJs in the ideal, and these guys generate the whole G tilde of A. Okay? So that proves that little lemma, that if you have an ideal that intersects with H non-trivially, then the ideal is the whole thing. So a corollary of this is that G tilde of A has a unique maximal ideal. So corollary, G tilde of A has a unique maximal proper ideal J inside of G tilde of A, which is included and is not equal. And that's now it's trivial because you just you look at the set of all ideals which are proper in G tilde of A, and you know that all of them cannot intersect H, because if they intersected H, then they are not proper. So any ideal of G of A, like the zero ideal, is such an ideal, which is properly included in G tilde of A, cannot intersect non-trivially H, therefore the sum of all of these ideals cannot intersect H, and that has to be maximal, because it's the sum of all proper ideals. Okay? So it's equal to the sum of all proper ideals. And it has to be proper because you're summing things that do not intersect H, so therefore this thing does not intersect H. So definition, G of A is the quotient of G tilde of A by this maximal ideal J, which is the unique proper maximal ideal. And this thing is a simple Lie algebra. Well, it's clear that it's a simple Lie algebra because if this Lie algebra was not simple, then I would just take this algebra by definition is a quotient of G tilde of A. It surjects here. So if this Lie algebra were not simple, then it would have a non-trivial proper ideal. And the pre-image of that non-trivial proper ideal would be a non-trivial proper ideal here containing J. And that breaks the maximality of J. So this Lie algebra is simple. Now suppose that you have a Lie algebra G whose Dynkin diagram or whose Cartan matrix, a semi-simple Lie algebra G, whose Cartan matrix is A. Okay? So if I have such a thing, then I claim that G tilde of A actually maps to G. Well, if the Cartan matrix is A, this is a semi-simple Lie algebra. This Lie algebra, we know by the theory of semi-simple Lie algebras that this guy decomposes as some Cartan subalgebra plus the sum of all the G alphas. This we know for a fact for any semi-simple Lie algebra. And now we choose a linear functional. We've checked that this linear functional does not impose any conditions. So, or that nothing depends on that linear functional, but that gives us a simple root space decomposition. And let's define this guy's EI to be the basis of G alpha I, some Fi to be the basis on G minus alpha I, and the HIs are the basis in H. So we find elements like this satisfying the properties that, well, since H is commutative, we always get this for free. Now we can always find EIs satisfying this equation.
And we can always find H, F, Hi, Fj satisfying this equation. And we can always find them satisfying this equation. The only one that is non-trivial is the last one. And you get this by the orthogonal, the fact that these spaces are one-dimensional and they are orthogonal, which I suspect Jethro must have proven already. So once you have these relations, then you know that this is a morphism. Because the same relations hold on this Lie algebra, they hold there. So you have a morphism like this, and this guy has a simple quotient with this G of A. So this guy exists. And you have this morphism of Lie algebras here, which cannot be 0 because the EIs, the FIs, and the HIs generate this guy. So this guy has to be an isomorphism. Okay, so we've proven that if the Lie algebra, if the finite dimensional simple Lie algebra G with Cartan matrix A exists, then it has to be this. Okay, because it's going to be isomorphic to this. Okay, and we know that there exists one Lie algebra, which is simple, and that it's coming from this Cartan matrix A, but we do not know that it's finite dimensional. So it remains to prove that it's finite dimensional. And that's non-trivial. That's actually highly non-trivial. So that I won't do today, luckily enough, because Jethro is going to have to prove the character formula. So it remains to prove. It remains to prove that G of A is finite dimensional. Okay, so I covered the lecture of today. We can stop here, and Jethro is going to pick it up next week. The proof that G of A is finite dimensional is highly non. So there are two things that are non-trivial today, and I haven't proven either. One of them is the fact that the free Lie algebra exists. The other one is the fact that this G of A is finite dimensional. So for free Lie algebras, I'm going to make one comment. We've checked that we constructed this G of A under the assumption that the Dynkin diagram was connected. But we never used the property of the Cartan matrix being Cartan. We've never used that the determinant was positive. So if you give me something that doesn't have a positive determinant, you still construct an infinite dimensional Lie algebra G tilde of A that has a unique maximal proper ideal J because of the same kind of arguments. And therefore, you have this quotient G of A. Now, for Dynkin diagrams that are not Dynkin diagrams of a Cartan matrix, but of an extended Cartan matrix, you get Lie algebras that are no longer finite dimensional. So the final dimensionality of this G of A is going to be a property of the Cartan matrix itself, being Cartan. But if you just take one of the extended diagram, these guys are infinite dimensional, and these are called Kac-Moody Lie algebras. And this is a very general family of Lie algebras. Essentially, anything that you can construct out of a Dynkin diagram of any form or a Cartan matrix of any form, if you take the Cartan matrix to be the extended ones that I explicitly constructed by adding one node, you get what is called affine Kac-Moody Lie algebras, and those are associated to the loop group of the corresponding group for G, for the finite dimensional G. The last comment is that in order to prove that G of A is finite dimensional, so that would finish the proof that these Lie algebras exist, what you do is you compute the character of G of A. So to do this, you compute the character
of G of A as a G of A module, and then you check that that character satisfies the composition, which is called the Weil character formula. And this leads to the fact that it's finite dimensional. So I'm hoping that, I suppose that Jethro is going to prove this in the next class. All right, so let's just stop right there.